The SLAM problem to be presented is taken from this paper, which has been published in IEEE Transaction and Robotics. So the problem this paper proposes a set membership approach to solve a SLAM problem. So simulation, range only, simulation and localization and mapping problem. So the test case to be presented corresponds to a robot which knows its initial position. Here, it is described by a state equation. So since it knows at the beginning where it is able to guess where it is in the future, but the approximation decreases, become less and less good. The robot knows that it is moving inside a map made, so the map is made with walls, with segments, but the robot does not know that the map is made with segments. The only thing the robot is able to measure, it's the distance between its own position to the map. So its own position to the nearest segment. So in the ideal situation where the robot knows exactly where it is, the reconstructed map could be something like this if the robot has this trajectory. So using a SLAM technique, it is possible to at the beginning to have a bad envelope of this trajectory and also an inner approximation of the map. But the inner approximation can help to decrease the size of the envelope containing the trajectory, and reciprocally, if you increase the precision of the trajectory, then of course you will be able to increase or to have a better approximation, a better inner approximation of the map in order to ideal situation to converge to this. As it is presented in this paper that could be obtained once the convergence has taken place. So let me show you here it is the envelope containing the trajectory. It is the actual trajectory of the robot, which is of course is not known, and here there are the segments here correspond to the unknown map. At the beginning, as we can see here, the robot is able to find an inner approximation to dig the space, but at the end, of course, it does not know very well where it is. That's why it is not able to dig the space anymore. It was not the case at the beginning, where the room has been dug in a quite good way. So from this, it is able to remove part of the trajectory that was not consistent with the inner space. That's why it was able, using the differential equation, to decrease the size of the envelope. And it starts again. So it has another simulation, and here, as we can see here, it is able to dig the space that it was not able to dig at the beginning, because here it has a better approximation where it is, due to the fact that some inconsistent values have been removed. That's why now the inner approximation becomes better and better. Here the track bar represents the time. So here initial time and final time. So at the end, when it will reach the final time, the track bar, so the pointer will be at the end. So it has soon finished, and then it will start again removing some part of the trajectory that are inconsistent. So we'll see it quite soon. Up here it was able to remove some inconsistent value in this envelope but the differential equation after the simulation will be able to propagate everywhere in order, as we can see here, in order to have a better approximation. That's why the envelope becomes thinner and thinner, and that's why now it is able to, as we can see here, to dig more and more the space. This process will converge to a fixed point. The fixed point is obtained after something like 10 minutes.